Hey everyone, Malio here. It seems like the newest TTYD any % task I made back in the summer has been very well received, and I can't be thankful enough to hear how much you all liked it. Over time, I began using more and more technical tools to help optimize my tasks further and further, and today is no exception. I'll be starting a 100% task for Paper Mario: The Thousand Year Door, and you can find all the criteria for this category over at speedrun.com/TTYD. One specific criteria for this category is cooking all 57 of Zest's recipes. She's the NPC that initially blocks the entrance to West Rogueport. Give her a new contact lens and she'll start cooking for you. Based on what items you give her, she can produce unique items. So, after all, the overarching question for tasks is, what's the theoretical fastest way we could complete this section? There are 57 different recipes that we need to cook, so naively, we could say that there are 57 factorial different ways to cook the recipes. However, there are multiple recipes which can be created using different combinations of items. If we ignore the fact that cooking certain recipes may remove required items from our inventory, there are more orders to cook recipes in than there are atoms in the entire observable universe. Thanks to several community members and myself, we may be significantly closer to finding out the optimal recipe order to potentially shave seconds off of the task. And we need your help. We've developed a program which randomly traverses down the tree graph of possible recipes and attempts to find the fastest roadmap. Upon finding the fastest roadmap known so far, the program will contact the server and submit the finished roadmap. This program can be located at github.com/7chords/cipes@home/releases. Under Assets, download the zip file corresponding to your operating system. If you're using Linux, download the source code and look at the README file to find out how to build it into an executable file for yourself. If you don't want to watch the rest of the video, I get it. We're gonna get pretty nerdy here, so if you're not into that, just download the program yourself and run it in the background. If you want to be recognized for finding the fastest recipe order, open config.txt and change default user to any username of your choosing. Also, if you find that the program is eating up too much of your CPU power, lower the worker count below the default of 4. Save, close, and then run the program. I'll go more into the specifics of content within the config file later on too, so if you're curious, stick around. If you're interested in the specifics of what led to this point, and why we're actually able to cook all 57 recipes in only 2 trips to Zest, please stick around to learn more. With all of that out of the way, here's everything you could possibly want to know about our little project, Recipes at Home. Let's first discuss a glitch that will save a ton of time for recipes called inventory overload. This is the result of a programming oversight exclusive to the Japanese version of the game. If you reach floor 50 of the Pit of 100 Trials and grab the Strange Sack, your inventory increases to a size of 20 items. Afterwards, using the key to unlock the blue puny cage in the Great Tree results in both the key and the Strange Sack being removed from your important items inventory. This reduces your inventory back to a size of 10. However, if you have more than 10 items prior to the removal of the Strange Sack, some interesting side effects occur. First, using an item in slots 11 to 20 causes the game to fail to remove the item from your inventory. The game recognizes that you do not have the Strange Sack, so it only attempts to remove an item if it's in the first 10 slots. Thus, if we have multiple recipes which require a particular item, we can place this item in slots 11 to 20 to use it multiple times without getting rid of it. Second, using an item in slots 1 to 10 gets rid of the item. This causes a weird side effect though. Because the game detects that you're removing an item, it brings all items forward in your inventory to fill the slot that you just used, up to and including slot 10. It then tries to mark that 10th slot as empty by placing item ID 0 in slot 10. We call these empty slots nulls. Because our inventory actually has a length greater than 10, this empty slot item is actually visible. Thus, there are now only 9 usable items in slots 1 to 10. Now, here's the weird part. Take a look at my inventory now and notice the Thunder Rage in the 20th slot of my inventory. If I use an item in one of the first 10 slots, then navigate to the second half of my inventory, the Thunder Rage disappears. The Thunder Rage is actually still there, but the slot itself is not being displayed, nor is it accessible. Because there's now a null in our inventory, the game detects that there are only 19 valid items in our inventory. Thus, it only shows the first 19 slots because it thinks all the items are contained within those slots. As long as there's a null in our inventory, the 20th slot will never be accessible in any context. If there are any additional nulls, then more items will not be available, starting from the 19th slot and progressing towards slot 11. Note that the hidden items can still be accessed if we sort the inventory. Third, sorting our inventory works normally even when we don't have the strange sack anymore. Recall that I said items in slots 11 to 20 cannot be removed upon use, while items in slots 1 to 10 are removed upon use. If we want to get rid of an item in slots 11 to 20, which is no longer required for any recipes, we can sort our inventory such that the particular item is brought up to the first half of our inventory. Using this item will now remove it from our inventory. Interestingly, if we sort our inventory while there are any nulls in our inventory, the nulls are moved to the end of our 20-slot inventory. This, by extension, means that hidden items at the end of our inventory will become visible once again. Note that if nulls exist when performing a sort, they're pushed to the end of our inventory and can no longer be tampered with. That is to say, our inventory size effectively gets reduced. If we have 19 items with one null in the first half of the inventory, then sorting the inventory will bring the null to slot 20, leaving us with an inventory of length 19. This length can never grow back to 20, so from this point onward, we can only hold a maximum of 19 items. Well, that's every detail of inventory overload, I believe. So this glitch is really useful for recipes. As you can probably imagine, we can exploit the effects of inventory overload to avoid backtracking for items. There are multiple recipes which require ultra shrooms, for example. Instead of grabbing 4 ultra shrooms across multiple long trips, we can instead just place one ultra shroom in slots 11 to 20 to use it 4 times without getting rid of it. We can use this fact for a bunch of recipes to reduce the number of visits to Zest's house down to 2 visits. You may be wondering if it's possible to cook all 57 recipes in a single trip, and sadly it's not. The mousse cake is required to obtain the dried bouquet through a trouble, and the dried bouquet is required for several recipes. The only way to obtain a mousse cake is by cooking a cake mix with Zest. Thus, we need to visit her once to cook some recipes, including the mousse cake, trade the mousse cake for a dried bouquet, then visit her a second time to cook the remaining recipes. We also need to grab certain items throughout Chapter 5 which are required for some recipes, so we can grab those in between the 2 trips. With all of that sorted out, let's first talk about why it's necessary to use a program to determine the recipe order. It takes a certain number of frames to perform various actions as we cook recipes, and they are as follows. It takes 56 frames longer to cook a recipe with 2 ingredients than it does to cook a recipe with 1 ingredient. It takes 32 frames to toss an item rather than have it get placed in the inventory due to an open slot. And it takes between 38 and 41 frames to perform the different types of inventory sorts due to opening and closing the pause menu. Clearly, we can see how much time can be lost depending on how many sorts are required, how many times we choose to cook a recipe with 2 items instead of 1, and how many times there is not a free slot in our inventory. Also, it takes additional frames to navigate to a particular slot in our inventory. This time loss will vary depending on how large our inventory is at any given point, but essentially, we want to avoid items towards the center of our inventory, as those items take the longest to navigate to, up to a maximum of 18 frames. Though we're talking about frames here, these numbers can add up a lot over the course of 57 recipes. We estimate that we would probably lose upwards of 10 seconds if we tried to construct a recipe roadmap by hand. So let's start talking about how we can begin modeling this problem into something we can program. So let's talk about graph theory. Graph theory is an area of mathematics in which you model the relationships between objects by representing each object as a node and representing the cost of moving from one node to the other as an edge. In our case, each node needs to represent the history of all recipes cooked as well as the state of our inventory. Given the sheer number of recipes, possible recipe histories, and possible inventory states, we can't just use 57 nodes to represent the 57 different recipes, which sucks because I really wanted to find an excuse to talk about the traveling salesman problem in a video. Okay, instead, we'll have to use a tree graph. Let's start with the root node, which represents that no recipes have been cooked yet, and it specifies our starting inventory. Underneath that are 57 child nodes, which represent the 57 recipes. If it's possible to complete a particular recipe, given our starting inventory, then we can draw an edge from the root to this child node, and specify the cost for this traversal to be the number of frames taken to complete this recipe. We can do this for all the remaining recipes to generate 57 child nodes, some of which can't be reached because we can't actually cook them. Then for each of the child nodes that can be reached, we can draw 56 more child nodes underneath those, and so on. What we're left with is a gigantic tree diagram that I'm not even going to attempt to visualize because it's so huge. Our goal is to reach the bottom of this tree diagram while accruing the lowest number of frames possible. Essentially, what we want to perform is a depth-first search. In this search algorithm, a program will traverse downwards until it reaches the bottom of the tree, go back up one node, then try going down the other child nodes. Once all of those have been tested, it then recurses back up a further node and visits the other children nearby. This process repeats until the entire tree has been searched. Obviously, given the fact that our tree graph is so large in this context, we cannot complete an entire search of this tree in any reasonable amount of time. Instead, we've opted to implement an element of randomness to randomly pick which children to visit first for any particular node. This way, on every new search, the program will likely wander down an unexplored path. With the graph theory explanation out of the way, let's talk about the actual inner workings of the program and some of the constraints we can put in place to reduce the search time. First, we have to initialize the starting inventory and the recipe list, which stores all possible item combos that are valid for each individual recipe. Then we enter the main algorithm loop. This loop is restricted to 100,000 iterations. The belief is that if we exceed this limit without finding a fast roadmap, this means that we're at a section of the tree graph for which there is no path below it that will yield a faster time. Thus, we treat this path as a dead end and restart the loop. We begin with the root node, which consists of our starting inventory and no recipes cooked. We iterate through each recipe, each item combination for each recipe, and each way of handling the output allocation. For each iteration, we have to determine if this is what we call a legal move, by which we mean that cooking this recipe does not prevent us from cooking other recipes later down the line. As long as it's still possible to cook the remaining recipes after performing this action, then we add it to an array of legal moves. One additional detail is that we cannot give Zesty the cookbook until after the first recipe. The cookbook is obtained during a trouble and grants Zesty the ability to cook recipes using 2 ingredients instead of just 1. This means that for our first move, we can only cook recipes which require only 1 item, so we can filter the rest out. Once we've iterated over all recipes, we then need to test if we can end our first visit to Zesty and travel to Chapter 5. Again, we need this break in order to trade the moose cake for the dried bouquet, as well as grab several required items from Chapter 5, such as the coconut and keel mango. If it's possible to go to Chapter 5 now, without preventing us from cooking the remaining recipes, this is also appended to the array of legal moves. After this, we evaluate all possible types of inventory sorts. These are treated as a last resort and are always appended to the end of the legal moves array. One detail with our legal moves array is that the fastest moves are always at the front of our inventory, excluding sorts. This way, it can be more likely to traverse down faster moves than to pick slower ones. Next, we have 2 config parameters called select and randomize. Select uses a methodology to randomly pick the next move to traverse to, such that it favors faster moves over slower moves. Randomize will strictly shuffle all legal moves in the array such that the next move is chosen at random without factoring in the frame cost of any move. Once the next move is chosen, the algorithm loops and the same process occurs for the new move. Interestingly, placing sorts at the end of the legal move array is nice in that sorts will most likely only occur if there are no other possible recipes to cook given the current state of the inventory. Next, let's talk about the config file. At the top are the select and randomize parameters. Setting them equal to 1 enables them, and setting them equal to 0 disables them. It's recommended to set at least one of them to 1. Disabling both of them means that the program will always wander down the same path every time you restart the program. Next is the log level, which is a value from 0 to 7. The higher the number, the more detail will be printed on screen. Increasing this number may degrade program performance, so it's best to just leave it at 3. If you find that there's still too much text being displayed, you can lower it to 2. Next is the worker count, which specifies the number of concurrent threads you want to run this program. This is set to 4 threads by default, but if you find that this is slowing your computer down, you can always lower it to 2 or 1. If you'd like to increase it, you can set it to a max of the number of CPU threads you have minus 2. Setting this any higher will likely heavily degrade your computer's performance. While multithreading in our case doesn't inherently increase performance, it is allowing multiple paths in the tree graph to be searched effectively at the same time. Lastly, we have the username. This username will be recognized if a new, faster roadmap is found. Feel free to change it to a username of your choice, restricted to 19 characters. Please be sure to leave the quotation marks around the username in the config file, as removing them will result in an error in the program window. In the event that you generate a roadmap personal best time, a file will be created in a subfolder. In the event that you discover the overall fastest roadmap, the file will automatically be uploaded to our server, and will be alerted that a new fastest roadmap was discovered by the username specified in the config file. Well, that just about covers it. Again, if you'd like to be part of the effort to shave off seconds for the task, please be sure to visit github.com/7chords/cipes@home/releases to download the program. I know this is a bit of an extreme project to work on simply to shave seconds off of a task that will be multiple hours long, but I'm incredibly humbled and glad to have had tremendous help from the following people to make this project possible. Cubik was the pioneer of this project and constructed a functional Python script to find recipe roadmaps. SevenChords stepped in soon after to help with writing portions of the script, managing our repository, and implementing multi-threading. Amphitryon jumped in a bit later, compiled Windows executables for the Python script, and helped debug certain issues we faced for the Python script. When we began porting this to C, Amphitryon was incredibly helpful in determining how to optimize particular functions and data structures to speed up the program. LEGO set up a server through which the program will submit the fastest known roadmaps, as well as create a webhook that has a Discord bot alert us when new records are found. Lastly, I have to say I had a lot of fun porting the code from the Python script to C language. I wanted to get more experience writing in C, and I can definitely say I'm a lot better at it now. Thank you to all these people for helping immensely. This project would not have happened without your effort, and I cannot thank you enough. And finally, thanks for watching.